AI to Connectionist AI and this back and forth movement will be done so that we look at all the important developments of. Please stop talking. So we'll be going back and forth from Symbolic AI to Connectionist AI, and this is necessary because we know that since the beginning of AI, there has been this parallel development, okay, of programming-based AI and data and learning-based AI. And when actually lots of data became available, for example, ImageNet for computer vision, ResNet for speech, then parallel data for machine translation, all the Symbolic AI systems were beaten hands down. Okay, there was spectacular performance by Connectionist AI, which was actually waiting in the background for 20 years, 25 years. Nobody believed that AI will be having such spectacular success. Okay, so it was surely caused by data, but we of course are also seeing quite a lot of plateauing in my field. For example, in natural language processing, I do see that very difficult problems are not solvable using only data and machine learning. For example, metaphor detection, sarcasm detection, they not only need data and machine learning, they also need a lot of knowledge input from human understanding. Okay, so there is also a very interesting paper by Ken Church, okay, who is one of the gurus of AI. The paper is called The Pendulum Swings Back. Okay, and in our class also we will do this swinging back and forth of pendulum. The pendulum swings back says that every 20 years there is a paradigm shift in AI. Okay, paradigm shift in the sense of choosing between one of the two, data and machine learning, data plus machine learning versus programming-based, knowledge-based AI. So every 20 years, the emphasis shifts from data and machine learning to programming-based AI and vice versa. Okay, so it really makes sense to look at AI from these two paradigms. Okay, and we should continuously keep them in mind. I do see that AI courses either emphasize one or the other, but it is important to take a balanced view, combining both Symbolic AI and Connectionist AI. Many AI courses now have become some kind of machine learning course, which is not right. Okay, we have to understand the basics of AI and they have a historical perspective of AI. For example, through search, logic. Okay, it is important to learn them and then connect them with machine learning and data. So we are now in what is called formal logic, where the ambition was to discover whole of mathematics from axioms and inference rules. One of the very interesting developments in formal logic was propositional calculus. And we started discussing Hilbert's formalization of propositional calculus, which I believe the class has not done in their course on logic. But it's a very beautiful example of how to attempt automation of an intelligent task. Okay, mathematical activity is supposed to be a very intelligent task. And there was this attempt of discovering whole of Boolean algebra, propositional calculus, from axioms and inference rules. So the axioms are extremely intriguing. How could somebody think of these as axioms? And only three of them. Okay, the first axiom is A implies B implies A, where A, B, these are templates. They can be instantiated by propositional calculus formula. For example, B can be P implies Q. A can be not P. Okay, and so on and so forth. The second axiom is A2. A implies B implies C implies A implies B implies A implies C. And the third axiom is A implies F is A. Now, implies F is given a shorthand notation of not. So this, the third axiom is intuitive. Double negation leads to positive. Okay, double negatives lead to positive. So A implies F is not A, and not of A is A. Okay, the opposite is also true. A implies F implies F, but that is not an axiom. Okay, and it can be proved from these three axioms, though it is an extremely difficult proof unless you apply what is called the deduction theorem. We are going to do that. Now, the opposite, A implies F implies F, takes about 4 or 5 pages of proof. Okay, and it's very cumbersome there. Now, these three axioms also have this interesting property that if you give them models, okay, instantiate A and B with 0, 0, 0, 1, 1, 0, 1, 1, then all of them evaluate to true. You can verify it for yourself. Though in Hilbert's system, there was no notion of truth. Okay, what was important was just probability. Okay? From the axioms, can you prove something? So let's look at the notion of proof. So let's try to prove that P implies P is a theorem. What is the meaning of a theorem? Theorem is anything that can be proved within the system using only axioms and inference rules. Just axiom and inference rule. Nothing else is allowed to be used. And the notion of proof is also very rigorous. Proof should be looked upon as a picture. Okay, it is a picture of steps, one by one. And every line in that picture is either an axiom or the result of applying the inference rule, namely modus ponens, on two previous lines. Nothing else is allowed in a proof. Okay, proof, your hands are tied. Proof is an extremely rigorous notion. It is a sequence of statements where each statement is either an axiom or or the application of inference rule, modus ponens. And then it was extended later. It was said that one of the lines can be also a previously proved theorem. Okay, previously proved theorem, because a previously proved theorem can be always expanded. Okay, and then it will again follow the definition of a proof. Every line is an axiom or the result of modus ponens. So let's look at the proof of P implies P. If something has to be a theorem, only axioms and inference rules and a previously proved theorem can be used in the sequence of proofs. So we start with P implies P implies P. Why? Don't know. Okay, it is creativity. Okay, now maybe I'll just try to see if ChatGPT can do this proof. I'll first ask ChatGPT, do you know Hilbert's axiomatization of propositional calculus? If it says yes, then I'll ask ChatGPT to give the Hilbert axiomatic system, and then I'll ask it to prove P implies P implies P. So theorems also are tautologies. Okay, they evaluate to true, but the discussion on tautology we will defer for a while because we are completely in a syntactic world. Okay, no reference to semantics at all. Semantics requires the introduction of a world in which meanings can be discussed. So please appreciate this point. Okay, suppose I have a sentence: the grass is green. Okay, now grass is green is a sequence of words. Does it have a meaning? It derives its meaning from reference to the outside world. Okay, the grass is green. The word grass conjures in your mind, okay, some green small objects which grow on the ground. All these things come by association to your mind. This is semantics. Okay, and then green is a color that also comes to your mind. And then green and grass, these two are linked by is, which you understand is an auxiliary verb. Okay, its purpose is to link. So this is called semantics. Semantics is impossible without the introduction of an external world outside the symbols, outside the symbols. So let's see P implies P is a theorem or not. P implies P is the usage of first axiom where A is instantiated with P, B is instantiated with P, A is instantiated with P. I am not breaking any rule. The first line is the result of the axiom. The second line is also result of axiom 1, where B is P implies P, A is still P. The third line is a result of instantiating axiom 2. P implies P implies P implies P. What is this? A implies B implies A implies B implies A, where A is P, B is P implies P. Implies P implies P implies P, A implies B, implies A implies C. Okay, so this is axiom 2. A implies B implies C, implies A implies B, implies A implies C. So this we have come up to this stage without breaking any rule, just instantiating axioms. Do you see some search being operational here? You have the option of choosing one of the axioms at every stage, or the option of applying modus ponens. So you are seeing that here is search in the background. So can you write an A-star algorithm, okay, which will choose the correct axiom and also decide between applying modus ponens or invoking an axiom to take you to the goal. What is the goal? Goal is this. The last line of the picture should be what we wanted to prove. In between every line is following the rule of proof. Okay. So we are performing an intelligent activity here. Can we automate this? Can we have a machine do this job? Okay. Then we apply modus ponens between 2 and 3 and derive P implies P implies P implies P implies P. Okay. So we have got this line P implies P implies P implies P implies P. This is modus ponens on 2 and 3, which is again obeying the rule of proof. And now modus ponens on 1 and 4, which gives me P implies P. So proof in a formal system is non-trivial. It involves search and making choices. Okay, so any question on proof? Suppose I ask you, okay, in anything, in any test or anything, give the proof of the following theorem. I'll be watching whether you have broken the rule any time in the sequence of the proof nuggets. Okay, so you have to, your hands are tied. We'll have to obey the rules, either modus ponens or axioms. This is the notion of proof. Any question? What is a proof? Okay, no. So anything, any structure which is which appears in the last line of a proof sequence, where every line is either an axiom or result of modus ponens, is called a theorem. Okay, so we have seen that the Hilbert's axiomatic system has the power to show that P implies P is a theorem. Okay, so this gives rise to an intriguing question. Any structure which I can create using the symbols and the rule of forming the structure, can it be decided as a theorem or not? Okay, by an algorithm. This is called decidability. give me any propositional formula. I will be required to prove whether it is a theorem or not. Does there exist a proof sequence where that structure is the last line? This is called decidability, okay, which I'm sure you have seen in your logic course. Is it the case that anything that is not a theorem still comes out as a last line in a proof sequence? Something which is not a theorem is proved to be a theorem by the system, then this system is called unsound. Okay, such a system is called unsound. And if there is a structure which is actually a theorem, but is not provable by the system, is called incomplete. Okay, all theorems should be provable, completeness. Anything that is proved should be a theorem, soundness. Any structure can be found out to be theorem or non-theorem, decidability. Okay, so decidability, completeness, soundness. In the lab, not now, after midsem, okay, you will be required to devise an algorithm which, given any propositional calculus structure, decides whether the structure is a theorem or not. And if you're wondering that if such a complicated process is involved of picking the correct axiom, deciding should MP be applied or not, can we really implement this in the lab? Well, there is a very nice theorem called Deduction Theorem, which you're going to see very soon. Now, here are a few convenient shorthands. P implies F is given this shorthand, not P. And it is given a name also, not P. Okay. You will have to keep semantics out of your mind for some time. No meaning associated. It is all a play of symbols. Okay, all a play of symbols. P implies F implies Q is not P implies Q. This is given a shorthand notation, P or Q. And it is given the name P or Q without any reference to the language sense of or. Okay, no such notion. It is all a play of symbols. Then P implies Q implies F is written as P and Q and is called P and Q. You can see that this is actually De Morgan. Okay, De Morgan operating on or. Now prove that A implies not of A using the modus ponens rules and axioms. It is a challenge. It requires 4 or 5 pages of sequence of lines. So these are the shorthands. So we have seen not operator, or operator, and operator. Now we come to a very useful theorem. We should call it a meta-theorem. Okay, because theorems are structures which are within the Hilbert's axiomatic system. This is a meta-theorem because it is a statement about the Hilbert axiomatic system. About. Okay, it says the following: if A1, A2, A3 up to AN can prove B, then A1, A2, A3 up to AN minus 1 can prove AN implies B. Notice that it is not a proof. It just says that if A1, A2, A3 up to AN can prove B, okay, the proof still has to be discovered. It is not saying anything about the proof. It is saying that if you can prove B from A1, A2 up to AN, then it is the case that you can prove AN implies B using A1, A2 up to AN minus 1. And this symbol, okay, bar and horizontal line is read as derives. So given a picture, A1, A2 up to AN and then B, where B is the last line, you can create another picture where A1, A2 up to AN minus 1, and the last line is AN implies B. So this is a very useful theorem because it makes life easy for proofs. So let us see the use of deduction theorem in proving A implies not of A, okay, which is the opposite of axiom 3. So the structure is A implies F implies F. This I need to prove. Now it's a very complicated proof for if you try to prove it from first principles, but apply deduction theorem. It is true that A and A implies F derives F. This is because of what? This is because of the modus ponens rule. Okay. If you have A and A implies F, you can derive F. Now just apply deduction theorem. So now A can derive A implies F implies F. Just shift the last line to the right hand side. So this is application of deduction theorem. And then I can shift A also to the right hand side. So I get A implies F implies F. So the proof is almost trivial. Okay, this is not a proof of A implies F implies F. It just says that A implies F implies F can be proved in the Hilbert system. Since it can be proved in the Hilbert system, it is a theorem. Okay, so you have bypassed the complicated route. So if you want, you find out the proof from first principles, but my job is done. I have shown that this can be proved in the system. So therefore it is a theorem. Okay, so deduction theorem is extremely useful, and you will implement deduction theorem in the lab, okay, using Python or whatever. So let's see one more proof. Let us try to prove P implies P or Q. P implies P or Q. So P implies P or Q can be written as P implies, you expand or is P implies F implies Q, because or was a shorthand. Now I can write P implies F and Q implies F derives F. Okay, because P and P implies F derives F. Now I keep shifting material onto the right hand side. So P and P implies F derives Q implies F implies F. This is deduction theorem. Now Q implies F derives Q by axiom 3. So now I can shift material onto the right hand side. So P and P implies F derives Q. So P derives P implies F implies Q. So P implies F implies Q can be derived in the system. So P implies P or Q is a theorem. Okay. So again, it is important for you to remember that this is not a proof. It says that proof exists. Since the proof exists, it must be a theorem. Okay. You on your own try to prove that P and Q implies P. Okay. Try to prove that P and Q implies P. Okay. Take this as an exercise. So we know that P and Q implies P or Q. P implies Q implies not P. De Morgan. P implies Q implies not Q implies P implies Q. These are, little involved theorems to be proved. So you should try to prove them. Okay. In particular, implement deduction theorem in the lab and give theorems and not theorems to be proved. So we have found a decision procedure in the Hilbert's propositional calculus system. That decision procedure is use of deduction theorem. Okay, so any questions so far? Okay, fine. If there is no question, then let's move forward. But do try to prove yourself these propositions, these theorems. So what is important to note is that deduction theorem is a meta-theorem. It is statement about the system. P implies P is a theorem, statement belonging to the system. Okay, this distinction is crucial in AI, and it takes us to the notions of self-reference, diagonalization, the foundation of halting theorem, Gödel's theorem, etc. So we discussed yesterday that many things in life cannot be proved. Okay, there are some stark examples. This statement is false. You cannot decide whether this particular statement is true or false. If you say it is true, then it must be false. If you say this is false, then it must be true. The barber paradox is also well known. A city has a barber who shaves all and only those who do not shave themselves. The question is, does the barber shave himself? This question cannot be answered. If you say the barber shaves himself, he cannot shave himself, and vice versa. Okay, so this is a form of what is called Russell's paradox. So now let's see what ChatGPT can do. Invisible to everybody. Okay, last bench. The screen is visible. Do you know Hilbert Axiomatic System for propositional calculus? Yes, the Hilbert axiomatic system for propositional calculus, also known as Hilbert system, is a formal system used in mathematical logic to derive theorems in propositional logic. It was developed by David Hilbert as part of his efforts to formalize mathematical reasoning. The Hilbert system is based on a set of axioms and inference rules. It typically uses a few axioms, schema, and a single inference rule, modus ponens, to derive conclusions. The system is minimalist but powerful and is one of the foundational approaches to formal logic. So axioms are here as I've shown you on the screen. Axiom 3 is different. X falso quod libet. Not A implies not B implies B implies A. This is law of contraposition. But in the original system, it is A implies F implies F implies A. Okay. And the inference rule is modus ponens. Derivations, example of derivation. Okay, completeness, soundness, all good. So now let me ask, then please prove P implies P is a theorem. Sure. Let's prove that P implies P is a theorem in the Hilbert axiomatic system. We will use the axioms and the inference rules to derive the formula. A1. P implies Q implies P. Same as what I gave. Axiom 1. Axiom 2. P implies Q implies R. Implies P implies Q implies P implies R. Proof. Use axiom 1 with P and P. Okay. So there's the first line. Then the second line. Now apply modus ponens. You get this. Apply modus ponens. Okay, it did not invoke. Oh, it did invoke axiom 2. Yeah, it is same as the proof given in the slides. Now the question is it retrieving that proof from the training data, or is it really proving it? Okay, that's the question. We don't know. Maybe somebody gave a proof of this and it went into the training data. The training data is all the time getting downloaded for training. And now that I have done the proof and it will go into the web. Okay, this will also be part of training data. Okay, now let me ask, prove that P or Q implies P and Q. This is not true, right? P or Q doesn't imply P and Q. The formula P or Q implies P and Q is not a theorem of propositional logic in the Hilbert system, as it is not generally valid. This implication says that whenever P or Q is true, both P and Q must be true, which is not true in general. For example, see what it is doing is that it is coming out of the axiomatic system. Okay, it is trying to assign meaning to P and Q by giving values 1, 0, etc. and then showing that this tautology or this implication doesn't hold. It is not within the Hilbert system. Okay, so in the exam, if you are asked to prove something, and if you draw the truth table and show that this is not a theorem or is a theorem, that will not be accepted. You will have to use only axioms and inference rules. Okay, and also in the lab exercise, you will have to use only axioms and inference rules and not the truth table. Okay, so you will have to remember this point that deduction theorem is a meta-theorem. P implies P is a theorem. Okay, meta-theorem is about the system. Soundness, completeness, and consistency. So in the syntactic world, that is with axioms and inference rules, you have theorems and proofs. In the semantic world, you have valuation. You give value 1 and 0 to the propositions. And then you create the truth table and see if the structure is a tautology or not. Tautology comes from the world of semantics. Proofs and theorems come from the syntactic world. If all theorems are also tautologies, we say that the system is sound. If all tautologies are also theorems, we say that the system is complete. So soundness means provability implies truth. Anything that is provable is also true. Completeness means anything that is true is provable. Okay, so completeness refers to the power of the system. Provability refers to the correctness of the system. Okay, proved entities are indeed true or valid. True things are indeed provable. Okay. Okay, now consistency. Consistency is a very important notion. The system should not be able to prove both P and not P. That is, should not be able to derive F. Okay, that is the notion of consistency. Any formal system that we propose should be consistent within itself. Now, this particular notion is really violated in the real world when we come to intelligent behavior. We know that human beings are not always consistent. Even the animals are not always consistent. Given the same input, the system, that is the living entity, does not always produce the same output. On the other hand, P and not P, if we allow both, okay, with a notion of probability or fuzziness, we'll do fuzziness also, fuzzy logic after some time. That's important for AI. And again, you'll have to implement fuzzy logic in the lab. So that will be a useful thing to do. Now we allow the system to be able to prove both P and not P with probability. Then we have a much more powerful system. Okay. So, however, let's remain in the formal system world. you will not allow a system to be able to prove both P and not P. Okay, so now at this point of time, let us do a little bit of philosophizing. Just think whether you believe in anything and also believe in its negation. Just introspect your, for 1 or 2 minutes and see if there are things which you believe and you also believe in the negation of this. Do you believe that sun rises in the east? You believe. Do you believe the sun does not rise in the east? You don't believe. So here is an example where you do not believe in P and not P both at the same time. Do you believe you will be rich? Do you believe you will not be rich? There is a possibility. Okay, there is a possibility. Do you believe you will get an A grade in this course CS217? Oh, I see. And do you believe that you will not get an A? Okay. So you see, we are systems, okay, which operate with lots of beliefs, and we keep them all the time alive in our mind. Okay, so real life intelligence is not consistent most of the time. It is a probabilistic world, and probabilistic world is modeled with probability, also with fuzzy logic. Okay, though fuzzy logic has not gone far, it is an interesting system of thinking about intelligence, which I'll do in the class. Okay, fuzzy logic should be done as an alternative to probability. Now, we would like to examine the relation between soundness and consistency. Soundness implies consistency. Okay, soundness and consistency are equivalent. Right. If a system is inconsistent, that is, if it can derive F, it can prove any expression to be a theorem because F implies P is a theorem. Okay. So very powerful statement, a very powerful system. A very powerful statement. Okay. Just pay attention to this carefully. If a system is consistent, that is, if you can prove F within the system, okay, then you can prove any expression to be a theorem. That is because F implies P. F implies P is a theorem in the Hilbert system. How do you prove that F implies P is a theorem? To show that F implies P is a theorem, observe that F, comma, P implies F derives F by deduction theorem. Okay. F and P implies F derives F trivially. I just reproduce F on the right hand side of the deduction symbol. Now I shift material onto the right hand side. So P implies F is shifted on the right hand side. So I have P implies F, which by axiom 3 is P. Okay, derives P. So F derives P, which means nothing derives F implies P. So F implies P is a theorem in the system. Okay, so so if a system is inconsistent, it can prove anything, absolutely anything. Okay, so an inconsistent system can prove, show that any structure is a theorem, which is actually not correct. Okay, very powerful statement. And see also how F implies P is shown to be a theorem. That's very instructive. Okay, especially this particular step, the first step, where F is just reproduced on the right hand side of the deduction symbol. Okay. Unsoundness implies inconsistency. Suppose we make the Hilbert system of propositional calculus unsound by introducing A and B as an axiom. So this is an interesting thing. Suppose you say that I cannot prove some structure to be theorem in the formal system. So what I say that I don't care. I'll just take that particular structure as an axiom. Okay, if I cannot prove it, I'll just absorb it in the system. So the effect of that will be that it will disturb the whole structure itself. So if you introduce A and B as an axiom, then the whole system will become unsound. Okay, so A and B and can be written as A implies B implies F implies F. If we assign F to A, we have F implies B implies F implies F. But F implies B implies F is an axiom. Hence, F is proved in the system. Okay, I hope you are with me that by introducing A and B as an axiom in the system, we have disturbed the whole system badly because the system has become inconsistent. Okay, so unsoundness implies inconsistency. If you have created a structure, you cannot simply introduce things into the structure, otherwise the structure gets disturbed. Inconsistency is a serious issue. Here is an informal statement of Gödel's theorem. If a sufficiently powerful system is complete, it is inconsistent. Okay, completeness and consistency do not go together. A very important observation obtained in 1930s, considered as another important foundation for AI. What does sufficiently powerful mean? It can capture at least piano's arithmetic. Okay, so our number system and in particular arithmetic with operators plus, minus, etc. were formalized by a mathematician called Peano. And Peano's arithmetic system is an example of a very well-known formal system. Now, any formal system which can capture at least Peano's arithmetic cannot be both complete and consistent. Okay, this is Gödel's theorem. Now let us, begin to have the AI flavor in all these discussions. Let us introduce semantics in the propositional logic. Here we introduce a very important function called valuation function V. The definition of V is as follows. V of syntactic false is equal to semantic false. Semantic false is Roman F. Syntactic false is Gothic F. Okay, so V of Gothic F is equal to F. This is a definition where F is called false and is one of the two symbols T and F. So valuation of false is false. Now we give the valuation of A implies B. It is defined through what is called the truth table. V of A and V of B are given. TF is defined to be F. Valuation of A implies B. If valuation of A is T, valuation of B is T, then valuation of A implies B is T. Valuation of A is false, valuation of B is false, then valuation of A implies B is T. Valuation of A is false, valuation of B is T, then the valuation of A implies B is T. So valuation of A implies B is false only when valuation of A is true and valuation of B is false. Okay, this you know from the property of implication. Okay, so this is how the valuation function is defined. So from this we'll move to tautology, and we'll also show that any theorem is also a tautology and vice versa as far as Hilbert's axiomatic system is concerned. Then we'll take up prologue and take up some logic problems to be solved by prologue. Okay, so this is the program for logic. Logic will continue after midsem also because I'd like to do fuzzy logic in the class. Okay, class is over.